The purpose of this lab was to use the principles of energy conservation, which relates to the loop rule, and current conservation, which involves the charge conservation and definition of steady state, in order to predict the behavior of circuits containing resistors in series and parallel. Another goal is to use multimeters to measure the actual values of the conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. We use the loop rule and the node rule to observe this behavior of the resistors and capacitors. The physics principles and themes include the following: energy conservation, the loop rule, which involves potential difference, the node rule, which involves currents, the change in the voltage measured in one round trip, and the function of capacitors in circuits. In this lab, we first predicted the current in a series circuit using the equation V equals I times R. V was 3 volts and R was 147 ohms. I was calculated to be 0.0204 amperes. Then I set up the series circuit in the virtual circuit construction kit. I connected ammeters so they read positive values. This is when the conventional current flows into the positive terminal. The ammeter reading matched the prediction stated previously. When the ammeter was inserted backwards, the reading was negative 0.02. Then I measured the potential difference where an ammeter was. Delta V was found to be 3 volts. The black end was connected to the battery, which has 3 volts, and the red end was connected to the wire, which has 0 volts. The leftover ammeter read 0 volts since the circuit was not closed and there was no current flowing. Voltage differences were measured in the different locations shown in the bottom image. The graph on the top left represents the general trend of the data measured. The addition of the voltmeter did not affect the current since it has infinite resistance and no current flows through it. Next, I added an ammeter in parallel with a resistance with 100 ohms. Both ammeters read 0.06 amps compared to 0.02 previously. This is due to the node rule. The current is now split between the 100 ohm resistor and the ammeter. Since the ammeter has 0 resistance, all of the current goes through the ammeter instead of the 100 ohm resistor. Therefore, the current only goes through the 47 ohm resistor. I then used potential differences in current to find the actual resistance of each resistor, the wire, and the ammeter, using the equation R equals delta V over I. The resistance of the resistor with 47 ohms was found to be 47.95 ohms, and the resistance of the resistor with 100 ohms was found to be 102.05 ohms. Both resistors of the wire and the ammeter were found to be 0. Next, I connected batteries to a 10 ohm bulb and capacitor in series. Then I disconnected the battery and connected the capacitor directly to the bulb. Next, I disconnected the capacitor to discharge it, and I repeated this process with a 20 ohm bulb. When charging, the bulb started off bright and the current flowed with maximum capacity. When T was greater than 0, the capacitor charges, the bulb dims, and the current slows down. With T much greater than 0, the capacitor is fully charged, the bulb is off completely, and the current has stopped. When discharging the capacitor, the bulb starts off bright and the current is at its maximum capacity. With T greater than 0, the capacitor is discharging, the bulb dims, and the current slows down. When T is much greater than 0, the capacitor is fully charged, the bulb is off completely, and the current has stopped. It is important to note that when discharging a capacitor, the current is reversed. For the 10 ohm bulb, the time to charge was 10.12 seconds, and the time to discharge was 13.99 seconds. For the 20 ohm bulb, the time to charge was 19.74 seconds, and the time to discharge was 27.86 seconds. These results make sense since the second bulb has 2 times the resistance of the first. This causes the time measurements to double as well. The next part of this lab explores the time-dependent voltage across a discharging capacitor using a circuit containing only a charged capacitor and a resistor. The following shows the plot equation, which will next be used to solve for RC, which is the time constant. T will yield a straight line with a slope of -1 over RC. This screenshot of Excel shows the data, the graph, and the line of best fit obtained. Voltage was recorded every second for 20 seconds, and ln of V over V naught was calculated using 8.8 as V naught. Then, by relating this natural log equation to y equals mx plus b, we were able to find RC. Since m, or the slope of the line, equals -1 over RC, we were able to calculate RC to be 6.906 seconds, which is close to the circuit value of 6 seconds. In real life, the ammeter would have a small amount of resistance, causing the overall reading from the circuit to be lower than the ideal value from this virtual lab. Using a battery to charge a capacitor without a resistor, the capacitor would be charged immediately once connected. In real life, all components, significantly the battery, would have some resistance, including the wires, which would increase the time it would take to charge the capacitor. Batteries also drain, and the equipment wears down over time.